All right. Good morning, everybody. We're going to go ahead and start. So, first off, before we get into the warm-up problem, I have a couple reminders for everybody. There is a weekly homework assignment on Wiley Plus that's going to be due on Friday. There's also exit slips due per lecture 1 week after the lecture is posted to YouTube. Okay, so today there's one due, and on Friday and Monday, Wednesday, Friday, and so on and so forth. Also, office hours have been a little bit quiet. I'd like to see more students coming. I see a lot of people on the exit slips listing things like, I'd like to see more examples of this type of problem. Unfortunately, given the amount of time that we have in class and the amount of material we have to cover, we have to go at a faster pace than would be perfect to get the most exposure to these problems. But office hours is a great time for you guys to come and see extra problems. Okay, so those are, yes?
Are your office hours only on Monday?
They're on Mondays and on Fridays. So on Monday, I have an office hour from 12 to 1. The link is on Blackboard. On Friday, I have office hours from 11 to 1. And there's a different link, which is also on Blackboard.
And that's on MTC?
That's in the MTC room, but it's typically empty of other students. So most of the time that I spend in the MTC, I'm dealing with my own students. Any other questions?
Is the homework due at 11:59 on Friday?
Yes, so homework slips, or exit slips and homeworks are always due at 11:59 of that day. Yeah, so you have until just before midnight to complete it. Any other questions? Okay, let's jump right into these warm-up problems. I think hopefully they shouldn't have been too much of a problem. We're just plugging in here. So for the sake of time, I'm going to go ahead and just write these out. For the first one, anywhere we see an x, we're just going to put a 2. So we get 2 times 2 squared plus 2 plus 1. They call this, quote, general form. I guess the goal of this is to try to get us kind of warmed up for what's coming, which is compositions. So later on, we're not just going to be plugging numbers into these parentheses, we're also going to be plugging bona fide functions into them. Okay, next one, pretty much the same deal. 2 times 1, 2, 3, 4, 5 squared plus 1, 2, 3, 4, 5 plus 1, and so on and so forth. Here we're going to get 2 times pi squared plus pi plus 1. Okay, then f of 21, same deal. Just going to expand this out like this. This is a bit tedious. Okay. So like I said, this is just kind of to get us warmed up for what's coming, which is going to be compositions. So I'll jump right into the definition thereof now. So a composition is what? An operation that takes two functions, f and g, and produces a function h of x equals f of g of x. Okay? So in particular, when we run h, our input is x. However, what we're really doing here is first plugging x into g and then plugging whatever we get out of g into f. Okay, so we kind of work our way out as we go. So I'll draw a picture of what's going on here because it can be a little bit confusing. So we'll return to our usual picture of the conveyor belt functions where we're moving left to right. And this is kind of like the setup that we have. So on the left-hand side, in goes x. And now, let me ask you guys, which function should go in this left box? Should it be f or should it be g? G, that's exactly right. We should put g in here. And what comes out the other side is going to be g of x. Okay? I know this is a little bit confusing because in our definition here we have f on the left side and g on the right hand side, but we got to remember that we work from the inside out. Okay? So g of x is then going to be plugged into our f box, and out pops f of g of x. And if we put this entire setup into a bigger box so that we couldn't see what was inside, then we would call that box H. So into H, we get x going in, and then on the inside, our x becomes g, and then our g becomes f of g of x, and then out spits, running out of space here, out spits h of x. Okay? So in particular, these last two things, f of g of x and h of x, are actually equal to one another. Okay, so let's do some practice. Before we do practice, are there any questions about the definition? Feel okay about it? All right, so let's try this. We're going to do the exact same thing we did in the warm-up problem, okay, where we just plug this in so-called general form, except this time we're plugging in functions into our parentheses instead of plugging in numbers. Okay? So our function here is x squared, and our inner function is x plus 1. So the way I'm going to write it is x plus 1 squared. Now remember, if I want to square this thing, I can't just distribute my square onto each of these numbers. Okay, what I have to do instead is write out, this is x plus 1 times x plus 1, and now what do I have to do? Anybody? If I have x plus 1 times x plus 1, starts with an F. Foil. Yes, exactly. Foil. So first we multiply the first things. We get x squared, plus we multiply the outside things. That's x here and 1 here. So plus x, the inside gives us x, and the last gives us 1. So we get x squared plus 2x plus 1. Okay. And we're going to get to this second part of this problem about describing in words how the graphs of the following functions differ. We're going to get to that a little bit later. So let's hold off on that for now. Let's just practice h and j. Well, this is going to be x minus 3 squared. That's x minus 3 times x minus 3. And that's going to be equal to x squared minus 3x plus 9 equals x squared minus 6x plus 9. Okay. Let me ask a question now. Is there anything going to be different about this last problem because of the pi? No, not much is going to change, okay? There's only going to be one thing that's a little bit different. Okay, so let's go ahead and do it. We'll have x plus pi times x plus pi. We're getting the hang of it now. We're going to get x squared plus, what do I get when I do outside? Multiplying these two. What should I get? How should I write that when I multiply those two things? We could write it x pi. Usually what we do if we have a number times x, such as x times 3, we usually write that as 3x with the number out front. Since pi is a number, we're going to write pi out front. So we're going to write pi x. When we do the inside, we're going to do the same thing. And then on the last part, we're going to get pi squared. That's how I'm going to write that last part. Okay. Now how do I combine these middle two terms? I'm going to get x squared plus something times x plus pi squared. What should go in my blank? Yeah, it should be 2 pi. Pi plus pi is 2 pi. Okay. Any questions about problem number 1? Okay, let's ramp up the difficulty a little bit. Let's try problem number 2. I'm going to start with A, and then we'll split ourselves up for C, B, and D. Okay, so the way that I'm going to do a problem like this is I'm first going to read the input from the very inside. That's my initial input. Then I'm going to plug my input into my function f here. And then I'm going to plug whatever I get from that operation into the function g. So, first I start with 6. So I go find where x is equal to 6. That's right here. Next I have to do f of 6. So I find the value of f when x is equal to 6. That's going to be 3. Okay? Now what I'm going to do is compute g of 3. So now I'm treating f of 6 as my input for g. G takes the input x, so I take x equals 3. So g of 3 tells me go to when x is equal to 3 and find the value of g at that time. Okay? So our final answer is going to be 10. Okay. Let's have group number 1 work on B. Group number 2, you guys can work on C. Group number 3, you guys can work on D. And group number 4, you can also work on D. You guys remember your groups? Okay. Okay, do we feel like we've had enough time? All right, group number 1, what did we say we were going to do? B? Okay, so does somebody want to walk me through how I'm going to do this? Sure, Ashlyn.
Okay, so I started with f of 4 and got 5.
Okay, so hang on, let me slow you down a little bit. So we read 4, we go to x equals 4, we find the value of f at that point and got 5. So we can write this as g of 5. Okay, good so far. Now what?
And then you do g of 5, which is 4.
Exactly. So then we read the input is going to be 5. So we go to 5, and we read the value of g is going to be 4. Perfect. All right, group number 2. Who wants to help me? Yeah, Mia?
Okay, so g of 2 equals 2, and then f of 2 equals -4.
Exactly. All right, last 2 groups, group 3 and 4. Somebody want to walk me through what I should do here? Yeah, Abhi.
So you go to 6,
Mhm.
and then you find g of 6 is 2, and then g of 2 is 2, so
Exactly. So perfectly fine for us to compose a function with itself. That's what this last part is telling us. We can do the function more than one time. So what that would look like is, if we had our conveyor belt in our box, we just, circle back, right, after we're done. We can just feed the number that comes out right back into the machine. All right. Any questions about problem number 2? Does that feel okay? All right. So now let's work on problem number 3 together. So what I really want to focus on is these ones, C, D, and B. Okay? So this first one we can do pretty quickly. We should just plug 2 into F. That gets us G of 3 times 2 minus 1 equals G of 5. We plug 5 into the other function, we get 1 minus 25, negative 24. Okay, same deal that we've been doing so far. But I want to talk about these parts here, okay? And these parts, we're going to use general form again. And all I'm going to do is, inside F, I'm going to write down G. 1 minus x squared. Now, I'm going to read from F here, and anywhere I see an x, I'm going to write this entire function in parentheses. So I will write 3 times 1 minus x squared minus 1. Okay, so I'm plugging a function into another function. Now I could simplify this by distributing the 3. We'll get 3 minus 3x squared minus 1 equals 2 minus 3x squared. That's how we would fully simplify that one. Okay. Now let's try doing it the other way around. This time we're going to take F and we're going to plug it into G. All right, I'm going to go a little bit faster this time. I'm just going to start off with the function g. I'm going to write 1 minus parentheses squared. And I know that what should go inside my parentheses should be the entirety of f of x. So I'm going to write down 3x minus 1 in here. Now when I square this, remember I have to FOIL. So I'll get 1 minus, if I were to FOIL this out, we would get 9x squared minus 6x plus 1. Now remember, this is all in parentheses. We square this thing. So we still have to distribute this negative sign here. So we'll get 1 minus 9x squared plus 6x minus 1. So our 1's will cancel. Our 1 minus 1 is 0, so those guys will cancel. And we'll be left with just negative 9x squared plus 6x. Why don't we have everybody try D on their own? And then we'll come back as a group. Okay, do we need a little bit more time? Feel okay? All right, does somebody want to help me walk through this problem? Yes, Ashlyn?
So I originally set it up as 3 parentheses 3x minus 1 parentheses minus 1.
Exactly right. And now what?
And then from there, I distributed 3 within the parentheses.
Exactly. We distribute the 3, so we get 9x minus 3 minus 1. And what was your final answer?
9x minus 4.
9x minus 4. Perfect. Anyone have any questions? Yes.
So why would the 3 be in front? Because I have like f of 3x minus 1 since that's what f of x is. Where'd you get the like 3 before the 3x from?
Okay, so we sort of skipped a step here. Let me insert something above this to see if it matches your work now. If I write f of 3x minus 1, and then I say that that's equal to this part, does that look more like what you wrote down? Yeah. So what Ashlyn did was skipped ahead a little bit, saved some time, and just went straight into plugging f in for x. I kind of like it when students write down this part first because it generally helps them avoid mistakes. So if you like doing it that way, I think that's good. If you can just go and look at the problem and plug it right in, that's fine too. Good question. Yes?
Do we solve for x or just leave it like that?
Good question. Okay, so the reason that we're not solving for x in these equations is we don't actually have anything to solve for. We would be able to solve for x if, for example, the problem said f of x is equal to 7. Then, at the end, we would have 9x minus 4 equals 7, and then we would move things around algebraically and solve for x. However, what we're doing right now is simply manipulating a formula. Okay, so all we're trying to do is express the formula in a different form using these algebraic equations that they gave us up at the top. Does that fully answer your question?
Yeah.
Any other questions? Okay. We're going to skip this problem and come back if we have time, but the next section is kind of a doozy, and I want to make sure I get through all of it. So ready your pencils because we're going to be writing a lot here. I'm going to talk about all the different types of graph transformations. Okay. So what are graph transformations? They're things like stretches, shrinks, shifts, and reflections. Okay, so we're going to talk about if we are given a function f of x, then we're going to write some things in and around this function, such as multiplying out front, multiplying on the inside, adding something on the inside, adding something on the outside. And those are going to change the way that our graph looks on the coordinate plane. Okay, so first what I'm going to do is I'm going to go through every single definition of how we get stretches, shrinks, reflections, and shifts, and so on and so forth. And then we're going to do some practice problems. So first of all, first thing, c times f of x. Okay, so if we multiply something out front, then the graph of f of x is ... And I'm going to do some cases here, okay? The first case is if c is in absolute value is bigger than 1, we stretch. Let me go back. Vertically stretch by a factor of c. Okay? If c is less than 1, strictly less than 1, we have a vertical shrink or compression by a factor of c. If c, let me say, if in addition c is less than 0 when we don't consider the absolute value of c, just the straight up value of c, if it's less than 0, so if it's a negative number, reflect across the x-axis in addition to stretching and shrinking. Okay, so that's kind of a lot of words there. Let's do an example really quick. If I start with f of x equals x squared, it looks something like a parabola. And if I were to say look at f of x equals 2x squared, the way it would look is if I literally just took like this, I wonder if I can even, if I literally just took this thing, man, it doesn't want me to deform it, does it? Okay, well, it's like if I literally just took that thing and I stretch it upwards like this. So in particular, every point on my parabola is now twice as high. Okay, that's what I've done. Every point on the parabola is now twice as high. So this is 2x squared. Okay, so that was an example of that. Next, we're going to do vertical and horizontal shifts. Let me first do f of c times x. It seems like a better order to present these in. Okay, so if I have c being multiplied on the inside, then the graph of f of x is, if absolute value of c is larger than 1, that's going to give us a horizontal shrink. Okay? Something that you'll notice when we do graph transformations is if we do something on the outside versus if we do it on the inside, it kind of flips our intuition on what we think is going to happen. Okay? So in the outside case, c larger than 1 corresponded to a vertical stretch. On the inside, c greater than 1 corresponds to a horizontal shrink. Okay? If absolute value of c less than 1, we get a horizontal stretch. And if, in addition, c is strictly negative, reflect across the y-axis. Okay, we reflect across the y-axis in addition. Okay, let's do a quick example. Hopefully I don't run out of time. We'll stick with f of x equals x squared. And what does that graph look like? Looks like a parabola. Okay, we shouldn't have used this example, should we? Let's think of a better example. Why don't we use something more complicated, such as sine of x? Okay. And for now, don't worry about remembering all of trigonometry. Just remember, or just keep in your mind for the moment, that the graph of this function looks something like this. Okay, the graph of our function looks something like this. Okay, so let's try something really wonky. We'll do f of x. Let's do f of negative 2, negative 1/2 x. Okay, so our c here is negative 1/2. Okay, so we know that it's going to correspond to a horizontal. Hang on a second, let's see here. Yeah, it's going to be a horizontal stretch, okay, since our c is less than 1. And then we've also got c less than 0, which means we should reflect across the y-axis. Okay? So the first thing that I'm going to do is my horizontal stretch. Okay?
You have to write, you have to negative 1/2 sine times negative 1/2 x into b.
This is how we can read that. So it just means we put in a negative 1/2 on the inside of our parentheses. Okay. So, first of all, we know that we're going to need to flip-flop this thing left and right like a mirror, okay? So let's do step 1, reflect. We get something which looks instead like this. Okay? It's going down initially and then up. Okay, so we did our reflection. Now, step 2, stretch. So what does it look like? It looks like if we just kind of dragged this thing out using our fingers. So if we put our finger here, and we put our finger here, and we drag the whole thing outwards, then what would it look like? It would just look more elongated. Okay, more elongated. Okay, so that's what it looks like. Okay, so here is this picture. Okay, questions about that one? Okay, we got a little more complicated with it. We also included a reflection this time. All right. Lastly, we're going to talk about shifts. So the first type of shift is a vertical shift. If we have f of x plus a, this corresponds to a vertical shift a units up. So example, we'll go back to f of x equals x squared. This becomes f of x plus a equals x squared plus, well, let's actually give it a number. Let's make it 3. F of x plus 3 equals x squared plus 3. Our original graph looks like a regular parabola. Our new graph looks like that same parabola, but shifted up 3 units. Okay, so this right here is 3. Oh, that's a bad 3. There we go. All right, vertical shift. Those ones are pretty straightforward. Second kind of shift, f of x plus a on the inside. This corresponds to a horizontal shift a units. And do we think it's going to be to the left or to the right? It depends on the plus or minus. Right now we've got a plus. So assume that a is some positive number and we add it. It's going to be going to the left. That's exactly right. Maybe I should say that's exactly correct so I don't get the words confused. Okay, it's going to be horizontal shift a units to the left. So in particular, if a is negative, then we go negative a units to the left. That means we move to the right. Okay, a units to the left. Okay, so let's have an example. If we do f of x equals x squared, we have our usual graph. And this is going to become maybe x minus 4 squared. Well, let's do x plus 4 squared for the first time. Okay, so since we have 4 is just some positive number, and we have a plus sign, we know we should shift this entire graph 4 units to the left. So what's it look like? It looks like this now. Okay, so we got moved to the left. Okay, I think I've fully classified now all of the different types of shifts and stretches and shrinks and reflections. The last thing I want to say on that, let me add a page in here, is the order in which we do them. Okay, so if we get something of the form a times f of b times x plus c plus d, where a, b, c, d are numbers. Okay, so they could be 4, 5, 6, negative 10, pi, all kinds of different numbers, okay? Now we're going to talk about the order in which we do these operations. So first we do C, shift left or right. Next up comes B, compress, stretch, reflect, horizontally. Okay, then we're going to do A, which is compress, stretch, reflect vertically. And lastly, we'll have D, shift up / down. Okay, so these are the order in which we want to do these things. And you'll notice it's fairly intuitive. We're going to do, basically, we're going to start on the inside of the parentheses, like we do in most things in math, and we're going to kind of work our way out. Okay. Let me pause for a minute now and ask, are there any questions about any of the graph transformations or the order in which we apply them before we move on to some practice? Yes, Ryan?
So like for B, if you're compressing or stretching horizontally,
Mhm.
like let's say like if it's 2, you're multiplying like the x values of the coordinates by 2 for the y value.
Let's see. So, yes, multiplying the x coordinates by 2. That's exactly right. Yes, so that corresponded to this sine example we did, where we basically just grabbed the end pieces and we just pulled it out as if it was a slinky, right? You know what happens to a slinky when you pull it out? It gets kind of stretched like that. That's what we're doing to our graph. Good question. Any others? Okay, I know that was a lot of writing and a lot of information to have at once. Let's see if we can apply it. All right, problem number 5, we're given this graph of f of x. This looks like the absolute value function, right? And we're supposed to apply these transformations and match with the correct graph. Okay, so why don't we have everybody try each of these problems, and then we'll go through all of them together. Okay, so try to match A, B, C, D, E, F onto these graphs, I, and so on and so forth. Would anybody like a little bit more time to keep going? Okay. All right, we all set now? Okay. Who wants to help me do part A? Well, why don't I do part A, B together, or we'll do A and B all together, and then I'll ask you guys about the rest of them. How about that? All right, f of x plus 1. I see a plus 1. Plus 1 here, and it's outside. Okay, outside means this is going to correspond to a vertical shift. The fact that it's a positive number means we're going to shift, what do we think, up or down? Up. That's right. So I just look for a graph in these boxes which looks like my original graph, but it's been moved up 1 unit. I think that looks like this one here. All right, for part B, we've got another vertical shift. We see this plus 3 out back. We know that's going to move us up 3. How about the minus 1 on the inside? Is that going to go left or right? Means we're going to go to the right. Okay, this can be read as f of x plus negative 1 plus 3. Okay, so we need to shift negative 1 units to the left. That means we have to shift 1 unit to the right. So I'm going to look for a graph that looks like we've gone to the right 1 and up 3. It looks like number 5 is matching that description. We went to the right 1, up 3. Okay, how about C? Who can help me with C? Yes?
You go to the right 2.
Exactly, just a straight up to the right 2. Okay, so which graph are we thinking?
I like this one.
Yeah, the first one. Exactly right. How about D? Someone else? Yeah, Andrew?
You would go to the left 2 and down 3, so it'd be number 6.
That's exactly right. Left 2 because we have a positive 2 on the inside. Down 3 because we have a negative 3 on the outside. That corresponds to this one here. So, you have VI. All right, last one, or last 2, what are we going to get? F of x minus 1. That's going to be the exact same thing as part A, except we're going to be moving down 1. Okay, so that's going to correspond to IV. And F here, we have plus 2 on the inside. That's going to be the opposite of part C. We're going to move 2 to the left instead of 2 to the right. Okay, so if we move 2 to the left, that's going to correspond to the last one, II. Okay, I think we'll call it there for today. If you have questions, feel free to stay after class. If you want to do an extra example or two, then we can do that, and I'll just keep the video rolling for the people at home if they want to get some extra practice. Mm-hmm. Ryan, you want to do a couple extra? Or you have a question?
It's on a different, like, it's on 1.7.
Sure, we can go look at 1.7 real quick. Ashton, did you have anything for me?
No.
Okay.
Thank you for extending.
Yep. Oh yeah, no problem at all. Was it one of these problems on this?
It's just like a general, it's some of the homework was difficult for me, so like when I have
Sure.
P naught times a to the t, how do I find a? I'm not really sure how to do that.
Okay, so you mean in the context of a word problem?
Yeah.
Okay, so let's go find a word problem here. Okay, let's take a look at this one here. Problem 1. This is a p naught a to the power t problem. So your question is, how do I figure out what a is? Okay, remember our definition of a was a is equal to 1 plus r, where r is going to be our percent interest. Okay, so if I were to read this problem, which says, suppose $6,000 is deposited into an account paying interest at a nominal rate of 2.7%, then my keywords in here are nominal rate of 2.7%. That is telling me that R is equal to 2.7% means over 100. So R is equal to 0.027. So in this case, the way that I find A is just by taking A is equal to 1 plus 0.027, which gets us 1.027. Is this the kind of problem that you were asking about?
No, I thought it wasn't. So it's like when it gives you 2 points and you have to create the function.
You're talking about this problem here, problem number 3, where we have an investment decreasing by 30%, and they don't tell us what P naught is.
Well, like on the homework, it was like, it would tell me like P naught, because P naught's just like 0, 40 or something, right? Like the first, like the y-intercept, isn't it?
That's right, yeah.
So it would give you like a y-intercept, and then it would give you like a point, like some random point, and like the function, and then it would have you find, like create the...
Ah, okay, I see. So you're talking about, this is something that we did in 1.6, I think. You're talking about, not converting, where are they? I remember what you're talking about. It might even have been 1.5. It's like they give you 2 points, like these problems.
Yeah.
Yeah, okay.
How to find a in that.
So how to find A in a problem like this, okay? The way to find it is, if we're given 2 points, so let's take this one for example, if we have 0, 100, and it looks like we're also given 3, 21.6. And we want to find the equation for these. Okay, first of all, we know that P of 0 is going to be equal to P naught times A to the power 0, right? Which means P of 0 is equal to just P naught. Okay, that makes sense. So that's telling us P naught is equal to 100. So we have our equation P of t is equal to 100 times A to the t. And here's where we're going to have to start incorporating our second point. Okay, we have 3, 21.6. So if I have this equation here, I can go ahead and plug in this point. Now, which one of these guys here is t? 3 is going to be t. So I'm going to write 100 a to the power 3. And on the left-hand side, I'm going to write what my value of p is going to be at that time, which is 21.6. Okay, so now the trick is just to take this algebraic equation and solve it for a. So right now, a is being cubed and it's being multiplied by 100. Which one should we get rid of first?
Cubed. No, the 100.
We want to get rid of the 100 first, because otherwise we would have to take the cube root of this entire side, and I don't really want to bother with taking the cube root of 100. So let's get rid of the 100 first. Divide both sides, we'll get 0.216 on this side, equal to a cubed. Now how do we get rid of the cube?
Like cube root it.
Yeah, cube root it or power
Or power of 1/3.
power 1/3, exactly. So 0.216 to the power 1/3 is equal to a. So that's how we figure out what a is. So if you type that into your calculator, you'd be able to find it.
So you just put the second pairs, like the second pair of the t value, you just like plug it in.
Exactly, yep. Yeah, once we get to this point, which, you know, our initial point is kind of how we get this, if they give us the intercept like that, which is pretty convenient. You know, sometimes they don't give us the intercept and it becomes a little bit more complicated to find A, but in this case, yes, once we have that equation, it's just down to plugging.
Is there one where they don't give you the intercept? That would be
Yeah, sure. So that would be this one here on the end. We'll do that one and then we'll end for today.
yeah, sorry.
Very good. Okay. So my 2 points are -2, 9.5 and 1, 0.5. Okay, so I know that P of t equals P naught times a to the power t. I know that P of P of 1 equals 0.5. I know that P of 2, -2, equals 9.5. Okay. So in this case, what I'm going to do is I'm actually going to take these two equations and I'm going to divide them to figure out what is going to be A. So first off, let me write this is equal to P naught times a to the power 1, and this is equal to P naught times a to the power -2. Now if I take these two numbers here and I divide them, do you see that the P naught is going to cancel out?
Yeah.
That's what we want. We want the P naught to cancel out because we don't know what it is from the context of the problem. But if we can cancel it out, then we'll have some number on the left-hand side, and on the right-hand side, we'll just have some power of A. Okay, so let's do it. We'll do P naught a to the power 1 divided by P naught a to the power 2. The P naughts cancel in -2. And that's all equal to, well, 0.5 divided by 9.5. Okay.
So a to the power of 1 is the same thing as P of 1? Or no?
No, sorry. What I've done here is 0.5 is equal to P naught a to the power 1. Okay? So what I initially did was, let me cross out these strike-throughs. What I initially did was I wrote really, and I'm getting too much highlighting going on here. What I did was this thing here is equal to this thing here. Okay? That came from these two equations. Okay, so P naught a to the power 1 is equal to 0.5. I know that P naught a to the power 1 is equal to 0.5 because of this point, which was given on the graph. Okay. Then I divided those two things with the specific intent of canceling these P naughts. Now if I cancel the P naughts and I have a to the power 1 divided by a to the negative power 2, what do I get? A to the something power. What should it be?
You like flip them, right? So 2 over -1, but I don't think that's right.
No, that's right. So, well, we don't flip, but if I have an power of x,
Oh, you subtract them, right?
that's right, I subtract them. If I,
Minus -2 is 3.
yep, perfect. And now do you know how to solve it from here?
I would take a point and stick in A.
Actually, we don't even need to do that. We have some closed form a to the power 3 equals 0.5 over 9.5. You can go ahead and plug that into our calculator. The right-hand side, we would get some number. And then what would we do to get a by itself?
To the 1/3.
Yeah, just take the 1/3 power. Exactly.
Thank you.
Yep, no problem. All right, stop this recording.